Okay, so this is the thin layer chromatography, or TLC, bit of a pre-lab briefing for you. So the first question we want to answer really is, what is chromatography? This is part one of a three-part set of chromatography experiments that you are going to do. Generally speaking, chromatography is a family of techniques that is aimed at separating mixtures of chemical components, or what we often refer to as analytes. So these analytes that we're looking to separate, they are usually in a mix, and we are looking to put them into a chromatography system, an instrument, or some kind of system that similar to the thin layer chromatography that we're going to do today, that we put together ourselves. And there are two key features that are shared by all chromatographic methods. The first is that there is always a mobile phase, and then the second is that there is always a stationary phase. So with these two phases, let's explain essentially what each of these things happens to be. So what's the mobile phase? The mobile phase is the carrier of the analyte, or analytes plural, that are being analyzed, identified, and or separated. And the mobile phase is typically a liquid or perhaps even a gas phase carrier. So in thin layer chromatography, what you're playing with here is going to be a liquid carrier. In your experiment for the TLC, specifically, you're using white vinegar. Vinegar is 95% water and 5% acetic acid, or at least the white vinegar that you have should be roughly that amount of ratio of acetic acid and water. The stationary phase. The stationary phase does the separating step as the mobile phase runs through it. So the stationary phase doesn't move. All right, it is stationary, it is stagnant. And it can be an adsorbent type of solid. It can be also a liquid that just happens to not be moving. So in the procedure that we're doing today for thin layer chromatography, we have an adsorbent solid that is stuck onto a thin aluminum backing, and it is a white coating on this sheeting. And so we're going to have to be very careful with the way that we handle it. Now, usually with thin layer chromatography, you have this solid support, and we have alumina. Sometimes it is also on a thick plastic backing. There are also TLC plates that are on glass. So there are different varieties of these things. Mobile phase can be really any number of carrier, what we refer to as eluents. And so they can be polar solvents to nonpolar organics. So we can also have mixed eluent systems. The mobile phase moves up the stationary phase by capillary action. So we are going to end up putting our system together, and the way that we are going to end up prepping and running our system is by using either, I'm honestly not sure what kind of TLC plates these are because they were provided in your kit, and I don't know what kind of TLC plates these are, so I may have to ask about that. They're usually something like either silicon dioxide coated chromatography plate. Alternatively, they can be what's called alumina, which is an aluminum oriented oxide type plate. Either way, they are oftentimes relatively polar in their orientation. So as far as being polar or nonpolar. So you usually have a coated chromatography plate that tends to be a little bit more polar versus nonpolar. It has something on there that has lone pairs of electrons that can have some kind of interaction with whatever you're putting on it. Now, your instructions are going to tell you that you need to mark an origin location on these TLC plates, and I demonstrate that in the video that follows. And that's going to be roughly 1.5 centimeters above the bottom of the plate. And you should make kind of gentle little tiny X's. It also instructs you to actually put a line at 1.5 centimeters from the top of the plate, because that's where you want to allow your eluent to run up to. So that is then called the solvent front or the eluent front. The way that this plate happens to be named, represented, in the event that you would be running an experiment where, let's say, you had perhaps multiple different eluents that you might be using, you might want to either make sure you're labeling the jar well, but then also possibly in the area that is not going to have any solvent run into it, you may want to even label up here in the top region somehow a code that would tell you what type of solvent system did I use on this particular TLC plate. Because there are other times where, there are experiments that use multiple different solvent systems to try and determine what might be the best solvent system for the types of analytes I want to check and analyze here. So you have an origin spot, and in the instance that's shown here, perhaps there's a mixture, and you may have perhaps a stock sample. Now, one of the most popular reasons for running, say, a thin layer chromatography plate in organic chemistry is because you want to perhaps analyze the progress of a reaction that may take a good bit of time. For instance, you might have a reaction where you're looking at, maybe the reaction between say something that has a benzene ring and another material that is going to make that benzene ring structure much bigger and more polar because of the type of substituents that are going to be added to the ring. So with that kind of a reaction, and maybe it's going to take an hour for that reaction to occur, you may want to decide that I'm going to look for my benzene ring on TLC plate, and I'm also going to test for, make a little spot for my other reactant. And if you possibly have some authentic product that you're expecting already available to you as a stock solution, and maybe you just have to make more of it, you might put that on a TLC plate as well, and you would end up measuring how far the spots move for each of those samples, and that way you would have an idea of what should your TLC plate look like when you only have, say, perhaps your benzene there, when you have a bit of your product starting to form, and when more of your benzene has disappeared and perhaps you have only your product on your TLC plate. So that's just giving you an example of when you might use something like this more commonly in a laboratory environment within chemistry. Now, how do we know, based on something as simplistic as thin layer chromatography, if what we're looking at is what we're expecting to see? Well, we look for something called spot resolution, or RF values, okay, resolution factor. And the way that we measure that is by using our plate. All right, so we've got our plate here. We have, as I mentioned, our eluent front is marked very clearly. We have our origin line marked very clearly. And then we also have our spots that ended up developing along the way. So this happens to be a chromatogram. All right, it's a TLC plate, but it is a chromatogram that shows the measurements for RF calculations. So the value S here, the whole distance from the origin up to the solvent front, is the distance that the solvent traveled. All right, and so that is often measured in millimeters. As long as you're being extremely accurate in the way that you're measuring, you could use millimeters or you could use centimeters. It's just a factor of 10 different. Frankly, it's not going to matter which unit you use as long as you are consistent in measuring both the solvent front and also the distance that your spot traveled, which here is listed as A, in the same unit. So and I'm used to just using millimeters, so that's what I tend to do. It doesn't matter to me which you do, but please be consistent. So what I'm looking for here is what fraction of distance did each of my spots travel. And so your values for your resolution factors should always be values of 1.00 or less. Okay, every single time it's going to be 1.00 or less. So in this case, for looking at the stock sample here, the measured distance was 25 millimeters. The full distance that the solvent ran was 55 milliliters, and so when that math is completed, the RF value is 0.45. Now, this is one of those few instances where you're going to have a unitless value as a reported result. And I will caution you that the best way to report results for these sorts of things is definitely in a tabular form, because it's just going to be so much simpler for your life to end up doing things that way. However, you do also have to show a sample calculation when you end up writing up the report for having done this experiment. So sample calculation is critical as well, just to show that, yes, I did do this calculation correctly, and then I will assume that all the rest of the calculations that you did were done the same way. So you don't have to show me every single RF value calculation, but please do show me at least one sample calculation so that I see that you did it right. All right, and the other thing that you would end up doing with this particular plate is then you would have, mixture, and you would show that, okay, this particular spot, maybe you would letter it or number it, you would identify it in some manner and have, that one listed as also having RF 0.45. And then this one would also be measured. Perhaps this one is at 50 millimeters, right? So you would take 50 divided by 55 and calculate that RF value. So what about these mobile phases? All right, and this is not at all an exhaustive list of the types of mobile phases that could be used in order to run these sorts of experiments. You can choose from any number of mobile phases, but these are some of the common ones that people have played with in the past. So least polar types of mobile phases, you're looking at things like cyclohexane. This is called petroleum ether, so really just, a mixture of ethers. Hexane, toluene, dichloromethane. All right, these are all things that are pretty much less polar. The more polar you end up getting, the more eluting power the solvent has. So what are we talking about eluting power for? So what does eluting power mean? Well, you may recall that I mentioned earlier that the stationary phase is polar. All right, so if you have a polar stationary phase, what does that mean for any analytes that are going to be on the stationary phase? It means they're going to want to stick to the stationary phase. they're going to want to hold on to that stationary phase if they are also polar analytes. So if you have an analyte that wants to stick onto that stationary phase, you're going to need something that is more polar in order to force it to move with the capillary action of the eluent. If you choose a mobile phase that is nonpolar, the only things that are going to move with the capillary action of the mobile phase as it moves up the TLC plate are the nonpolar analytes. So if your analyte mixture happens to have molecules that are less polar, those are the only ones that will move. So you can actually change the order and the RF factors of your analytes based on just changing the mobile phase. Now, something else to remember. If you do go and change a mobile phase, you cannot any longer use the same RF value calculations, right? RF calculations are only good for a particular system that you are using. So if you decide, for instance, that you're going to use a specific TLC plate type and you are going to do all of your analysis with ethanol as your mobile phase, then that is fine, and all of the RF values you calculate will be suitable for doing that analysis with those chemicals with that particular type of plate and using ethanol the whole time. Your RF values should not change. It will not matter how long the plate is, what distance you allow things to the eluent front to move. The RF factor will always be the same. And so that's the other nice thing about TLC, is that it doesn't matter if you allow the solvent front to go 50 millimeters or if you allow it to go 100 millimeters. The ratio of movement of your analyte will always be, if it's 0.45 for 50 millimeters, it's still going to be 0.45 at 100 millimeters of distance. You'll have to have a pretty tall jar in order for that to occur, but it's going to be the same. Okay, so you typically want to choose an eluent that has the opposite properties of the stationary phase, that separates analytes differently than an eluent with similar properties. But, caveat to that, it also depends on what kind of analytes you're working with. So for instance, the experiment you're going to do, we're using a water and acetic acid mixture. Water's really polar, all right? So what does that tell you about what's happening with the washable marker inks? All right, if they're washable markers, they're supposed to be able to come off of clothing and hands and pretty much anything with washing, with water. So they're probably going to be more polar types of dyes and such that are included inside of those markers. Okay, so that means that we're going to use water and acetic acid, essentially vinegar, as our choice because that is probably going to give us the best separation. All right, the developing chamber, another key component to how this is all done. Now, if we were in a lab, usually you may use, you might, let's say, construct a developing chamber from various equipment that's in the lab. However, if you weren't going to make a developing chamber from equipment in the lab, you may actually even already have a TLC plate developing chamber. They do build those things specifically for that purpose. What we're going to do is use the little plastic container that had been used for the previous week's experiment of doing the liquid extraction with the mineral oil and water containing blue dye. If for any reason you happen to have disposed of that, what you're going to do instead is find yourself a jar of approximately that size that's going to fit your entire TLC plate into it, and use a piece of plastic wrap instead so that you are able to cover it and put a rubber band around it or something around the plastic wrap to kind of keep all the contents inside, right? So how is the developing chamber constructed? Okay, first of all, we've got this container that is going to certainly hold the mobile phase at the bottom. Okay, so there's your mobile phase, the solvent mixture. Um, the thing that was not included in the instructions initially, and it still is not included in the instructions, but I ended up doing this myself. Oftentimes, we also put a filter paper that is soaked in mobile phase and adhered to the walls of your chamber. So I ended up cutting a piece of paper towel and adhering it to the walls of my chamber, not so that it completely covered the inner walls, but enough so that it kind of surrounded in like a semicircle, so that I could still see my TLC plate developing, because that's really important to still be able to see it. And so white paper towel, no color in it, mind you. Didn't want to end up complicating things at all. And so I put the paper towel in there, and I had poured in my 15 milliliters of vinegar. And then I just turned the chamber sideways so that it would wet the paper towel entirely. And then I gently put it back upright and closed the lid. Now, why would I want to put that in there? Well, kind of the same reason you always want to put a cover over top of your TLC chamber. The cover is going to maintain a stable solvent to volatile solvent atmosphere inside. Okay, so why might that be important? So the paper or paper towel acts as a solvent wick to help saturate the enclosure, all of the airspace, also with the solvent vapor. Why is that critical? Depending on how much organic material is actually in your solvent system, you know that organic chemicals tend to be much less polar and therefore much more volatile, right? They have lower boiling points. And so as your solvent is running up your TLC plate by capillary action, the further it gets away from the liquid, the more likely it is to also start evaporating off of your TLC plate. So what's going to happen? It's going to slow the process of your analytes moving up the plate, and you're going to end up possibly having analytes running into each other a little bit that maybe otherwise would be better separated, because you're going to have like faster movement at the bottom, and then everything's going to slow down as it gets up to the top of the plate, because your mobile phase is disappearing. It's no longer there if it starts coming off the plate and evaporating. Whereas if you have a solvent wick, essentially paper adhered to the side that is soaked in your solvent, that stabilizes that saturated atmosphere so that you no longer have this active exchange and active evaporation of solvent off of your TLC plate. So that way you have a more consistent and constant capillary action of your mobile phase up your TLC plate. And so the cover is also critical in that, so that your atmosphere is stabilized on the inside. One of the other things that is mentioned is that your spot for your markers is going to end up being at the 1.5 centimeter mark above the bottom of the plate. And there's a really good reason as to why do we want it above the liquid line. All right, and so you need to consider, why should it be above the liquid line? What is a good critical reason for that to have happened? Why do we want it there? What makes that a critical thing? All right, so that's pretty much all I need to tell you at the moment as to the nitty-gritty of why, the whys of how thin layer chromatography is set up. It is stressed that you should wear gloves when performing any of the TLC experiment and handling any of the plates. Think about what kinds of things could be on your hands but not on the gloves when handling plates. So those are also some things to consider. And at the moment, I think that's about it. Any other questions that you might have, don't be afraid to, again, look in that Williamson PDF file of organic experimentation and reference that for thin layer chromatography and any chromatography technique for that matter, because I think that is going to be a valuable resource to you going through the remainder of the semester. All right, that's all I have. Okay, students, so here we are once again with a video to show you essentially what should happen with your TLC experiment, thin layer chromatography. So what I have in here is a not perfectly well printed out set of directions in black and white for this experiment. I also have, of course, a pencil. I've got my TLC plates taken out. I've got a ruler that does have metric units. I retained my jar and cleaned it out well and dried it thoroughly from doing the experiment for the extraction. I've got my setup here for my graduated cylinder. I've got distilled white vinegar. It says 5% acidity. Well, that actually just means that it's got 5% acetic acid. And of course, the washable markers. I put everything here out on a paper towel just so that I'm getting my space covered. And it looks like that's pretty much everything I need. I do have the gloves on. Excuse me. So yeah, everything that's listed here is intact. So one of the things that it directs you to do, regardless of whether you're using a glass jar, if you happen to have disposed of this, is to take your TLC plates, and since all of mine are about the same size, and just make sure very carefully that it does totally fit inside of your jar. All right, and so mine does completely fit in, as you can see, from top and bottom. Fabulous. All right, then the next thing that we need to do, make sure that we measure on both sides of the plate about 1.5 centimeters from the bottom. And then we want to put a mark on either side of the TLC plate. Now, when we do this, we have to be very careful about doing so because the TLC plates themselves are really just sort of this silica gel material, as it's called, or aluminum oxide often, that is very delicately adhered to this backing. And so we don't want to press too hard with our pencil. As a matter of fact, I'm going to switch which pencil I'm using. The one that I have here is actually a drawing pencil, and then you see HB on there. It's actually a pretty hard lead type pencil. So I'm going to get one that has a softer lead from over here. All right, so this one is going to be hopefully a softer lead. It actually says HB on this one too, but we'll see what happens. All right, and so on your plates, you want to, again, do your markings from the bottom by 1.5 centimeters. So that is what I'm doing here. Okay, so I'm going to mark one of them up for now. And then the other things that you need to do. We are going to lightly draw a straight line between the two tick marks, again with the pencil. And this is going to be the origin where we're going to make our spots. And then we're going to put two very small little X marks equidistant from the sides of the plate and each other on that origin line with the pencil. And this is where we're going to spot each mark. We're going to use the purple marker. All right, so purple marker. And also we're going to gently touch the tip of the marker to the first X. And we want to do this just once, okay? And then we're going to also use the green marker and touch its tip lightly on the second X and touch it just once. Now, a couple of notes here. One of the reasons that we are doing the X is to really just make sure that we know exactly where we're touching that tip. Secondly, the reason that we're going to only touch it gently to the TLC plate. One reason is, again, we don't want to disrupt and end up accidentally flaking off the coating. And then secondly, we don't want to oversaturate the coating that is on there with our marker. If you push down too hard or you do more than a light touch, you're going to get a spot that instead of, if this is, let's say my TLC plate line, and I've got my gentle little X's here, if you push down too hard, one, you could certainly scratch the coating, but secondly, your spot is going to spread out tremendously. And if that happens for both spots or even just one of them, they could start to meld together in the middle, and that's going to mess up your readings. The other thing is if a spot gets spread out too much, as it does start to move, it's going to be much more difficult to read because it might start continuing to spread out a little bit. And that's a process called eddy diffusion. And you're probably going to learn about that as you start doing some research. All right, the other thing that you want to do is also measure, as the directions say, 1.5 centimeters down from the top of the plate on each side, make little tick marks. And of course, you're going to draw a line across with your pencil from one tick mark to the other. That's going to be what we call the solvent front line. All right, once we have that set up, we are going to charge our container with 15 milliliters of vinegar, put the plate inside, and with the spots end pointing down. And from there, make sure that the vinegar level is below the origin line, all right, especially if you end up having to use a different plate, or I'm sorry, a different jar. If you end up using a different jar that's not of the same dimensions as this one, you definitely want to be especially careful of that, okay? And so for now, I'm going to stop this video and rejoin you in a few moments once I get everything set up. Okay, so I'm back with my TLC plates all ready to go. One of the things that I did was to choose my markers. I, of course, set up my various TLC plates here. I have my purple and green. I put my spots here on my plates. I put spots here as well. I decided my second plate I'm going to use black and red. Now, something that I decided to do to deviate slightly from the procedure, and you can choose to do this or not, but normally when we do this sort of procedure in a laboratory environment, what I also have students do is I have them put a piece of filter paper inside of the chamber for developing the TLC plate. And what that filter paper does is it is then adhered to the sides of the chamber, much like this piece of paper towel is. So I cut a piece of paper towel that is roughly the height of the jar, and it certainly dips down into, you can see it dips down into the solvent, which is really water with acetic acid in it. And it has also fully absorbed the acetic acid, so it is wetted all on the inside. Now, what this typically does, especially if you're using an organic solvent, is it allows for the organic solvent to fully saturate the atmosphere inside of the chamber in which you are developing your TLC plate. So this can become really important when you're developing a TLC plate, and I will either have explained that prior to you viewing this particular segment of the video or in a separate video and giving you information separately. I'll do a little bit of a separate lecture that gives you more detailed info. So what I'm going to do now is take the lid off of this jar, and I'm going to add my spotted TLC plate here that has the purple and green on it. Actually, you know what? I'm going to use the black and red instead, because I'll let you see what purple and green does on your own as the graded item. Now, one of the other things I want to show you. So the plate that I'm going to put in there, you can see that it kind of has an already dug out scar, if you will, along the edge, and a little bit all along that particular edge side. So what can this possibly do? Well, it might cause a little bit of an issue with the way this plate runs. So we'll see what happens. All the way at the top as well, because the plate got a little bent in shipping, you can see that there's a little bit of a scar up there too. So I may actually end up stopping this plate before it gets to that drawn line. So we'll see what happens though. All right, so you have to very carefully put the plate in and drop it into the solution, and then you let it go. And then we're going to put the lid back on also carefully so as to not just disturb the whole system. All right, we don't want to force any of the liquid to do anything too wonky. But you can see how we end up having the liquid just run up the plate entirely. Now, I know there's a little bit of parallax or something going on here. That's just because of the droplet that's on there. So the interesting thing about the black marker is that you can see it's got a number of different colors that end up being mixed into it. You know, right away you see, similar to the red marker, sort of this color of red that starts running up. All right, so you can see some other colors starting to also kind of come out of it as we try and sort of refocus in there. All right, so maybe there's a little bit of blue in there as well. Okay, and this is going to take some time for all of the development to occur. All right, this fighting against gravity issue is going to be prevalent sort of the whole time through. So, you know, we have to keep that in mind as this process moves on. All right, so I'm going to stop recording again rather than keep this going the whole time through, and you know, we'll see what the end result looks like once this one finishes. Okay, so this particular plate is finally done, and what you will notice is that we have gotten to the line. While it's sitting here to dry, it likely is going to continue running a little bit further up the line. The other thing that you can do, because there's at least initially going to be a little bit of excess on the bottom, is you can kind of blot off the excess by gently sort of touching it to the edge of a paper towel like that. But other than that, what you need to do is be patient and let it sit. Now, the whole time that took, once I put it into the jar and for it to then completely run, I will be honest with you, it took about 20 minutes for that to run. So I'm not telling you that you can just walk away entirely and ignore it, of course, but you do have to be mindful of the amount of time that it will take for that to fully run. Now, you do have to let it dry completely before you start marking anything on it. So you want to definitely do that, but you may also want to snap a picture or two while it's damp, just in case there are any little spots or something that are visible now that might not be visible once it dries. For whatever reason, that could maybe happen. So that's my advice to you on that for the moment. All right, so I'm gonna let this dry, and we'll come back in a few moments.